same thing I told ya. My eyes are clear, there's no secret. I wanna know, was it serious? I need it clear. My best friend isn't easy to show, with the weight of the world on my shoulders. I know I told you, it's the best light I know. It's not a game that I am playing. My love, trying to hold my feeling. I don't know what's right. I'll find the best way. I think that I might. I know you made it in the nick of time. I'm calling on you. I think we're made of something. I think we're made of something. I keep my time in a pocket.
Okay.
I wanna find a new keeper. I like the way it's mysterious. I think I found my own way. Isn't easy to show, with the weight of the world on my shoulders. I know I told you, it's the best light I know. It's not a game that I am playing. My love, trying to hold my feeling. I don't know what's right. I'll find the best way. I think that I might. I know you made it in the nick of time. I'm calling on you. I think we're made of something. I think we're made of something. Trying to hold my feeling. I don't know what's right. I'll find the best way. I think that I might. I know you made it in the nick of time. I'm calling on you. I think we're made of something. I think we're made of something.
Okay. All right. Good afternoon, everybody, or good evening wherever you're at. Hello, hello, hello. Hope everybody is doing well this very fine day. All right. I will probably be posting something on the screen here. There we go. Hopefully everybody is doing well here today. I'm gonna be going over some more question and answers for anything and everything related to some statistics and whatnot, or any other questions in and along the way. Go ahead and go over to my main screen here. Go to the big board. Here we are. Alright, so should you have any questions or just want to pop and say hello, talk about something, not a problem. Here just to get stuff done, I'm sure. So, sure that a lot of you have questions, I'm sure. So, I'll just be waiting here for a little bit. Oh, there's Gemma back again. Hey, yeah. I'll thought you had gone to bed. So I'm like, it's close to midnight there. Hey, Susan, good evening to you. How are you? Good evening, good evening, good evening. I'm sure that maybe you have some questions there. Remember, Susan, you got 4 days until the third test has to be completed if you haven't done so already. So 4 days until the third test has to be completed there. So be sure to finish that by the end of the week. I'll probably be sending out a email reminder regarding that. Hi day, hello, good evening to you. How's it going today? Hopefully doing well. Go to the main screen. I'll go back to the chatting screen here for just a second. You've been watching Andy, the stream finished. Very good, very good. Hopefully Andy is doing well. I was eating and just relaxing a little bit before this next stream. So more questions to answer means I need a bit more energy, you know. Energy. Hopefully his stream went well. Even I saw him he was playing Valorant, so there you go. Yes, you have questions. Okay, good. Glad you have some questions there, Heide. I'm here to hopefully answer said questions. The word contingent on hopefully. Usually I do, but, well, you never know. Questions can easily come out of left field, and then you're like, Alright, you got one right away. So, oh, did somebody beat me to a gift sub? Aww. I was gonna gift you a sub there, Gemma. I'll do it next month there, Gemma. I promise you that. Let's go to the big board. It's a 9-1, question 4. Okay, let's go. Question 4. Okay. A national survey of 1,500 adult citizens of a nation found that 20% dreaded Valentine's Day. Margin of error for the survey was 3.1 percentage points with a 90% confidence. Explain what this means. Okay, so 20% of people dreaded Valentine's Day. So basically, you're 90% confident. There's 90% confidence that the proportion of adult citizens of the nation dreaded Valentine's Day between 0.169 and 0.231. Now, the way you get that is just basically subtracting 3.1% from 20% and adding 20 to 3.1% since that's your margin of error. So that is should be A here for that, and that's correct. All right, so that is the answer there for 9.1 number 4. I'm happy about. I gotta be quick. You're right. I do have to be quick about it, Gemma. You got that right. That's all you gotta do for 9.1 number 4 there, Heide. That wasn't too bad. 9.2 number 4. Hey, what are you doing to me? You're killing me here, Smalls. Telling me wrong sections. Sheesh. No, I'm just kidding. Let's see, 9.2 number 4. Ah! Alright, I'm gonna need to make this a bit. Okay. So it says the data shown on the right is representative in weeks is at which babies first crawl of a survey based on 12 mothers. Complete page A through C. Alright, let's do it. So part A, draw a normal probability plot to determine if it's reasonable to conclude the data comes from a population that is normally distributed. Choose the correct answer below. Okay. Well, what we do need to do here first, before we can determine this specifically, is we need to first take out our calculator here. All right. Did I like your message, the paragraph one? Oh, yes, 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 the one you sent me on Discord, yes. That was very kind of you. Very super kind of you, Gemma. Really super kind. Alright, now what I need to do here is make sure that it's not covered up. I hope the music is not too loud here. If the music's too loud, I can turn it down. So just let me know. Alright. So what we're going to do here is we're going to make a list. So let's make a list here. Okay. So we'll hit clear. And clear here. And we'll go ahead and put in all the numbers in this data set. And we'll take a gander here at what we have. Okay, so these are our numbers here. What we're going to do here specifically is we want to go ahead and take a look here at pretty much what the standard deviation, the mean is going to be, you know, things like that. And then we can probably get a good guess about which one of these it's going to be. So let's go to calc and go to 1var stats. We're just going to use the first list that we have there. Gemma, Gemma, you're super kind to me. Always, you know. The feeling is definitely mutual, Gemma. And I thank you for your extremely kind words there. Hey, Major Man. How's it going? Alright, so the mean here is 40.25. Okay, so we have a standard deviation here of 9.8. Okay, for this, alright, so there's sample standard deviation. So let's take a look here. What would be our z-score here? So our z-score would have to be positive above a 40.25. You know. Just got done writing a discussion about math anxiety. Oh, it's actually definitely a thing. I always try and solve that by being as easy as possible. You're the best, Gemma. All right, so we have absolutely 100% agree, Gemma. That's why I like full disclosure. So a higher expected z-score would be the higher age in weeks. So it's going to be either C or D here. It's going to be one of these two guys. And let's see what the difference is. Is there a difference between C and D? There doesn't seem to be much. Oh, right. The expected z-scores are what's different. So what's the z-score here for... What's the highest one? 56. Alright, so 56. So we could find out the z-score for this. We're going to take 56 minus 40.25. Then we'll divide that by like 9 point something. I'll just fudge the numbers here. So it should be around 2-ish. Alright, so I'm thinking that probably C is probably going to be the one. Or not C, I'm sorry, D. D is going to be probably the one. So let's check that since the z-score is here around 2. Yeah, that's correct. Okay, good. That's all I expect you to be, Gemma. Just be yourself. And the current self that you have there, Gemma, is a fantastic one. 100%. Is it reasonable to conclude that the data comes from a population that is normally distributed? In this case here, I would say yes, the plotted values are approximately linear. Okay, check that. Yep. All right. Moo indeed. Hello, JD. Draw a box plot to check for outliers. All right, so if we draw a box plot, our mean here, as we saw in our 1var stats, let's go back here for just a moment. I'm going to go back to my calc here, go to 1var stats. And we have, first of all, a median. We can check out some of the stuff here. We have a median of 37. So we want to have at least this guy here have a median of 37. So C is out because that does not reflect a median of 37. That doesn't even have a median. D is out because that has a median that's above 40. That's this middle line right here. It cannot be B because, again, B would be above a 40. So your answer has to be A based on your 1-bar stats. All right, so you have, let's check our answer here. That's correct. Does the box plot suggest that there are any outliers? And the answer to this is no. There is nothing really outside of the boundaries. So 26 maybe. I don't think there is a point actually that's outside the boundaries. So I would say no. Okay. All right, so we got the first few parts done here for A, and B here. Okay. Okay. So, are we good there so far, Ide? Okay, cool stuff. All right, now let's go to part C here. Part C says to construct and interpret a 95% confidence interval in this instance. Okay, so that's what we're going to do here. We're going to construct a 95% confidence interval. Now to do that, we're going to go ahead and hit the stat key here. We're going to go over to tests. Hey, Natty. Good evening to you, Natty. And we're going to go down to specifically what we want to do here for this case is we're going to go down to T interval, okay? T interval is going to be our guy here for this particular problem. We are going to enter in data here because we do actually have a data set. In this case, we're going to let the calculator deal with all these super exact values. So we're going to hit second and 1 for our list number 1. Our frequency will be 1, and our confidence level will be 95.95. Hit calculate. And so we'll have, we are 95% at the mean age. The baby first outside is within. So we want to pick B because we want the word within the confidence interval. So that's kind of important. We want it between both numbers. 1 decimal place is what they want here. So 34.0, 46.5. Okay, we'll check that. And we got it. And that's how we could do part C for number 4 from section 9.2. Heidi. There we go. All right. Nice. I see the next one here was JD with 10-3, number 1. Didn't I do that one already? But I'll do it again. Are we doing that one again? I thought I'll be happy to do it again. Small brain moment. Oh dear. As 10-3, yeah, 10-3. Sadness, lots of sadness. Oh, okay. Where are we stuck on here? I did this with you already here, but let's do it again. I showed you how to do it. Didn't you follow what I said? All right. Yes, degrees of freedom is n-1. That's true. So tell me, let's take a look at what we have here, all right? So we have a hypothesis test here. We're doing the t-test, okay? That's what we're doing, the t-test, all right? Let's talk about this. Doing the t-test. Okay. We're putting in stats here for the t-test. We're keeping the mean here is 100. We have x bar here is going to be 104. Standard deviation is 9.2 with a sample size of 15 and a two-tailed test according to this. We go to calculate here, and we do have our test stat here. Our test stat here is going to be 1.684. All right, let's go one at a time, JD. You're cool with finding out that first part there for letter A, right? Are we good with letter A, JD? Okay. Now, to find the critical values by hand, we're going to need two things, okay? Let's talk about this. We have a two-tailed test, okay? So because you have a two-tailed test means to split, you need to split the significance level in half. So you have to take 0.01 and divide it by 2, which equals 0.005. All right? Then, you also need to find degrees of freedom. How many degrees of freedom do we have here, JD? We have 2 degrees of freedom. Try again. How do you find degrees of freedom? You wrote it down already. You said degrees of freedom is n minus 1. So tell me how many degrees of freedom we got. Okay, what's n? Look at the problem. What's n? Okay, very good. That's correct. All right, 14. Good. I'm going to make you answer it this time because I already did this once. Being mean. All right. Now I'm going to click on this chart here. Okay? Now this is where this chart going to come into play. All right? That's okay, Gemma. Don't worry about it. Don't worry about it. It's okay. All right. So you're going to look underneath the column that says 0.005. And you're going to look on the left-hand side for your degrees of freedom, which is 14. And you're just going to line up the number here. And that number specifically is 2.977. Now, since this is a two-tailed test, you need both the positive and negative values. We had some adjusting to do because we have a two-tailed test. So our critical values here, 2.977 and negative 2.977. Okay? All right. Good stuff. So far, so bueno. So when it's right, it's only... So when it's to the right, it's... So if it's to the right, it's going to be positive. If it's to the left, it's negative. So right should be... I should have said right positive critical value. Alright, since we have a two-tailed test, we're going to click on letter C. That's a two-tailed test on both ends. Hey, Katie. We're going to click on that. There we go. And then, will we reject the null hypothesis or not? Well, clearly in this case here, 1.684 here, or actually even the p-value here, 0.11, is still going to be bigger than 0.01. So there's not sufficient evidence to reject the null hypothesis here in this case. So, unfortunately for us, it is not happening. I think it is. Oh, it's not between? No, it has to be between. Okay. For critical values, it does. No problem, Katie. Take your time. You're always welcome in here. So, if it's between both critical values, it means it's not sufficient evidence, essentially. It has to be within this blue region in order to qualify, basically. All right. And that's what we get here. All right. That is problem number section 10.3, number 1 again. All right. This time you should know how to do it if you had run into a similar question. All right. All right, we good, JD? I got no problem with that at all. 9.2 question 6, okay? Athena asks. Go ahead and take a look. I don't mind what you ladies do. It's all good. Oh, thank you for the hydration station. Appreciate that. All right. It's worth. All right. All right. 9.2 question 6. Okay, good. Drag this over here. All right. Well, a doctor wants to estimate the mean HDL cholesterol from 20 to 29-year-old females. How many subjects are needed to estimate the mean HDL cholesterol within 2 points with a 99% confidence, assuming S here is equal to 19.4 based on earlier studies? Okay. I suppose the doctor would be content with 95% confidence. How does this decrease here? So let's should be like a, yeah, okay, these are just critical values here. All right, so all we're gonna need here is oh, Katie says to say something nice. Okay, Katie, you're a wonderful person who takes care of a lot of young kids and are a vital, important cog in the community. You should be very proud of the work that you do, even though a lot of times a lot of people may say we're underloved or underpaid. We do it for the care and the love that we know that we want to support, not only for ourselves, but we want to support the community. So wonderful job, Katie. You do a great job out there. Gemma, you have star attraction written all over you, and I'm crossing my fingers and toes and full 9 yards. That way you can hopefully get yourself up off the ground. I believe in your talent and I believe in your ability, and I think you'll make a wonderful actress in the future. There we go. All right. Let's go ahead and take a look at this one here. This one here. Athena, thank you for the 100 bits. That's really super kind of you. I don't deserve 100 bits. Thank you. My goodness, thank you, Athena. That's really super nice. Man. Oh man. I don't know what I could do without this community. I don't know what I would do. You guys are super nice to me. Even my own students are nice to me. And that's rare. To a math teacher, that's rare. Even I think that's rare. Some days, I tell you. I deserve it all. Some days I kind of wish I did. I'm trying to be a good positive influence in the community, regardless of what community that you're part of right now. Why did I buy it? Because it was a two-tailed test, JD. That's why. My name is Chins. That's fine. I have like 30 of them down here, okay? Trust me. My name is Chin BS. I have chins and I'm full of BS. Oh man. It kind of goes together based on how big I am. Double steak chipotle? You bet. Ah! Oh my goodness. That's a laugh and a half. You know, you gotta be comfortable about who you are. You know, when you get up here, you're like, it's fine. It's fine. You know, it's perfectly fine. I understand. I have the double possible double chins, and the possible tsunami waves I make when I roll over in my bed. Just kind of those. My bed kind of goes flappity flap like this. I'm like, yeah, I've made it. All right, so we just need to use a formula for this here. All right, so the formula we're going to use for this here, specifically Athena, to answer your question. Oh my word! All right, I'm gonna bust out the paint tool for this one. So the it's just gonna look like this here. We have the crit value times the standard sample standard deviation divided by the margin of error, and we're just gonna square it. So this is kind of this problem here, admittingly, is more of a throwaway problem, but just for the sake of just covering our bases, I just put it in here. Let's see here. So what's the critical value here? Well, we have a 99% confidence level. So a 99% confidence level, according to this, is going to be 2.575. Okay, so let's use that. So for 95% anyway, or 99%, 2.575 would be correct. Okay. Oh, I didn't click out of that problem. Pretty bad. Probably did. Oh no, I didn't. Okay, that's good. All right. We have times S. S is 19.4. And we'll divide that by the margin of error here, which is 2 points. Yeah, so 0.02. And we're going to square that whole shebang. Okay. Says Mr. Chibs, I have to go to an appointment. Okay, a very important one. Okay, that's fine. I mean, I don't have a problem with that. If you have a very important appointment with Mr. Sandman, that's perfectly fine. Yeah, honestly speaking, I used to sleep in class all the time when I was like back in the day. The margin of error was given to us here because it says within 2 points. So that is the margin of error here. That is given to you in the problem, Athena. I mean, that's very true. I was too insecure to sleep in class, Yeah, I wasn't. I wasn't. A lot of students got mad because they saw me sleep and they said, "How could you get away with it?" I'm like, "Yeah, I just do." Then again, I had some other issues. So I'm like, okay, I still got away with it. All right, let's go ahead and put that in the calculator. So we got 2.575 times 19.4. We'll figure out what this is first, and we're going to divide this by 0.02. Then we're going to take this answer and square it. Okay, so we be sure on the... Oh, let me check one thing here, actually. Let me check one thing here, I'm sorry. Give me just a second here. This answer seems rather large. Athena. We want 2 standard deviation points, or do we want just 0.02? Oh, okay. Alright. Alright, I got it. Alright, so ignore this. I thought we're working with percentages, but we're actually working with straight points, okay? Yeah. I was thinking, I'm like, that seems a little high. I should have something like in the 2,000, 3,000 range, but not something that would be like 400,000 or so, or even 4 million. Alright, so we have to divide by 2. We're going to use the straight up value here of 2 because 2 is referencing the value here for that. What do you have to be sorry about? Nothing to be sorry about? That's cool. I fell asleep in exam by accident. I woke up and was so embarrassed. Oh, that's fine. Like, I finished the exam, but it was still... Oh, that's okay. Look, I've done a lot of embarrassing things in class. As a student, as a teacher. Both served for very good memories. Let me try this again here. 2.575 times 0.4. We'll divide that by 2. And then we'll square that. That looks a lot better. Then we'll square that. So our answer here will be 623. For my answer here is 623.8788. But we round up, of course. So rounding up, we will take 624. And that's going to be our final answer for at least this part here. Oops. What was our answer here again? 624. We got 624 here. Bada bing, bada boom. Now we just repeat the problem here once again for the next one. 95% though has a different critical value. That's going to be 1.96 according to our table. So repeat this with by changing out the... So you're just going to be taking 1.96 times 19.4 divided by 2 and squaring it. So same exact problem here, just with one slight different variation. You are behaving. I don't know, see what the problem is. Clearly you've never been... You gotta be in my class to understand that throughout the years of the nearly 20 plus years of teaching, I get myself into a lot of bit of trouble when it comes to my classes. I've done enough crazy things in my classes to know that probably it was too silly to get away with. Yeah, appointment with your bed. Tell your bed it should behave better. I threw my shoes across the room once. Does that count, JD? Not at my students, of course. Why? Because they felt uncomfortable and I didn't want to wear them anymore. So I just wanted to go barefoot the rest of class. Just out of sheer feeling. That's a true statement. Sometimes I just kind of felt like it. I'm like, yeah, you know, I don't want to do it. I don't want to do it. Okay. Why? Because I can. $361.45, okay. So 361.45 is what I got here, so up to 362. Yeah, make myself at home. Another time, it was Halloween, right? One of my students decided to dress as Dick Tracy, right? Yeah, the big trench coat and everything. Now, he thought he was really smart, so I'm like, okay, fine. I'm like, this is easy. I'm like, you know, I was introducing a trig concept, right? So I was like, all right, you know what? I'm not going to go over this problem. I said, you know what? You could go over this problem. You could teach the class in my stead. So I switched places with them, put my feet up on the desk, sat back for the next 20 minutes, and said absolutely nothing outside of just correcting them every once in a while. Best 20 minutes of my life. AF. All right, 362 is the answer to that one. All right. How does decreasing the confidence affect sample size? Well, you just decreasing the confidence level decreases the sample size, of course. So there you go. Easy peasy. And that's going to be section 9.2, number 6. All right. That's what we got for that problem there. All right. 9.2, question 5. Sure. I love Q&A. It's so fun. No problem. I'm here to help. Let's go. It's question 5. Okay. All right. So a trade volume of stock is represented. Trade volume of the stock is the number of shares traded on a given day. The data in the company table in millions. So the 6.04 represents 6 million plus shares traded. Fine. Represents the volume of stock traded on a certain day. A random sample of 40 trading days in a certain year. All right. Second random sample of 40 days in the same year resulted in data in the second accompanying table. Okay, so we have first sample and second sample. Fine. All right, so let me click the data here. All right, so there's the first sample and second sample. Use the data from the first sample to compute a point estimate for the population mean of shares traded per day in the year. Okay. All right, so all we're going to do here specifically, Heide, is we're just going to go ahead and take that data set we see here. Let's plug that into a list, and let's see what we're working with. All right, so we'll hit the stat key. I'm going to go over to edit. Let's clear out our list here. So let's go ahead and put in all the numbers in here. So a lot of this is kind of busy work, just due to all the numbers that you kind of have to enter in. All right, I'll take that question next here once I'm done with this one here. Let's see. All right, so I put in all 40 values here from this first list. All right, I got it. Yeah, all best. All right. Now that we have that set and ready to go, let's go ahead and take a look here and see what we got for our data set. So we'll hit second and quit. We're going to go ahead and hit the stat key. We're going to go over to tests, okay? We're going to go down to T interval here, okay? So T interval is going to be the way to be, Heide. So we're going to take, of course, data here in this instance because, we have a complete 40 thing data set. So our confidence level here in this instance is going to be, we could pick any confidence level to get the point estimate. Okay, even though I know they don't really have one, we're just use the default value of 95 because the point estimate, no matter what confidence interval that you choose, is still going to be the same regardless. All right, so we're going to hit calculate here. Now our point estimate here in this instance is going to be this guy right here, this X bar, which says 4.4445. So, oops. You spit water all over your English teacher. Oh no. Well, how did it get to that point where you spit water all over your English teacher? Do 4.445. 4.445. Check this. And that's correct, okay? So that's how I was able to find the point estimate. Doesn't matter what percentage that you choose. Now, in this case, they do give you a percentage confidence interval, which is a 95% confidence interval. So if you want to go back and do it again, you can. I know we did it already here for this, but just in case, do the T interval. Again, you just need to change this confidence level to the confidence level indicated in the problem, which is 95%. I yelled at my teachers when they wanted to test me, but why would you yell at their teachers when they wanted to test you? That's like the point. Trying to kind of get you to do, like, see how well you fare in your aptitude of the material. So in this case here, let's see here. We're gonna take letter B here. Letter B here basically says 1 can be 95. Oh, whether it's sassy, okay. Well, what exactly what kind of sass? Because everybody's got a different definition of sass. So we have between 3 point, how many decimal places do they want here? 3 decimal places, okay. So 3.922 and 4.967. All right. I was laughing at something. I had a mouthful of water. My teacher stood in front of me and I sat in the front. Yeah. Oh dear. Oh, I picked the wrong one. Sure. Let me read that again. What could be 95 of the mean shares of stock traded in all days? Shares of stock traded per day. Oh, okay. Whoops, I picked the wrong one. Okay, try that one. 0.922. Yeah. 4.967. Okay, I just picked. Read the wrong one. So in this case here, Heide, I picked C because it's the number of shares traded per day in the specified year instead of the all days. It's not all days, it's just the number of traded per days in the specified year there. That's a good story though, I have to say. Using the data from the second sample, construct another 95% confidence interval. Alright, so essentially it's just a repeat, only you're doing a different data set. So, we're going to pick this here. One could be 95% confident. And then we're just going to plug in, we're going to make another list of data. Okay. Ide. So let's go through the second sample. We're just going to write down, type in the values for this. On that highly embarrassing moment, head out. Oh, okay, Gemma. You have yourself a wonderful night. Okay. And I will see you again, possibly tomorrow. I'll be having a stream here a little bit later at night for you, but I will be here, so answering some more questions, of course, or doing whatever because I'm an idiot. So we're gonna go with that. I hope you have a wonderful night, Gemma. And thank you for coming on by, okay? Have a great night. Take care of yourself. All right, so we got all the values put in here. I just went over that slowly. And we're just going to go ahead and take a look here and do the same t-test and all that, t-interval and all that jazz. So let's do it. Hit the stat key. Just because they're 40 values here, Heide, you just got to be careful of the values you put in. So just kind of go slow. The t-interval here, we'll put list number 2 in this case, L2. And we want a 95% confidence interval. Calculate that out. And so here in this case, we get one can be 95% confident that the mean number of shares of stock traded per day in a specified year is between 4.018. Will there be that many on the test? I mean, I did the if I pulled the test, I basically made the test directly from the homework, so that's a possibility, yes. I'm just going to point it out that way. That's a possibility. I don't want to lie. And we got it. Perfect. So, sadness, possibly. That's a possibility, yes. Explain why the confidence intervals obtained in parts B and C are different. Well, not only are they different, they're different samples. Samples have different means and standard deviations, still leading to different confidence intervals. I mean, yes. So, I mean, they're different samples, so of course they're going to have different stuff. So, I got to be truthful, though. I got to be truthful at times. This is one of those times. If it's on the test, it's on the test. But I pulled it directly from the homework, so should want to be at least 100%. I want to be at least transparent about what's going down. All right, very good. All right, so that's going to be 9.2, number 5. All right, next question. Yes, of course, you can send me a screenshot, Natty. Go ahead. Write in Discord. Can a p-value really be 0? Yes, a p-value can be 0. Or maybe really, really tiny where it's basically approximates to 0. Because p represents a probability value, right? So probabilities can take on a value between 0 and 1. So technically, yes. Otherwise, it's just like so small that it basically rounds to 0, you know? Like if you were to round to 4 decimal places about winning the lottery, you know, that would technically round to 0. I don't know what you did wrong because I don't know what question you're working on there, JD. No problem. Yes, the p-value should show up in the t-test unless it's really tiny. Oh, there we go, Natty. All right. All right, so construct for that. Okay. Natty, which problem was this again? Could you tell me? I want to see the. I want to take a look at that. Screenshot of screenshot. That's fine. Oh, you didn't see the E? Yeah. Yeah, the E makes a big difference there. What problem is that, Natty? I'll take a look at that problem specifically. Okay. Check it out then. Let me check this out here. Careless. Need to be able to skip around here for a second. That was. I want to say that was chapter 9. That definitely is chapter 9. Every single problem from the question. Yeah, it was chapter 9. Okay. All right. I'm going to go over this question here, Natty. I found the complementary question to that on the homework. That was section 9.3, number 2. Okay, so let's go over this question here. I'm just going to kind of... I'll go over this question here so that way we get this down. All right, so a simple random sample of size n is drawn from a population that is known to be normally distributed. Sample variance s squared is determined to be, in this case, 12.8. Complete parts A through C, which is very similar to the problem that you have here on the sample test, the practice test. Construct a 90% confidence interval. All right, I'll get to that here once I'm done with this, JD. So construct a 90% confidence interval for that squared if the sample size is n is equal to 20. Okay. And in this case here, we were able to kind of replicate that here, but I saw in your case that unfortunately was not happening. Okay, so what we want to do here specifically, and I need to reference one thing, reference something here. Just need to make one confirmation. Right, okay, that's fine. Okay, so This one here had stuff to do with we had two formulas, if you kind of remember how this works. Now, I'm going to kind of show this off here from the notes here, Natty. All right, so just remember, this is from our section 9.3 notes. That was using the sample size here of n-1 times the variance here, divided by the critical value, and you had two critical values here, critical value 1 and critical value 2, depending on the confidence level that you were given here in the problem. Okay, so this one here had that more unusual formula associated with it for this particular problem. So be sure to write this formula down so you can reference back to it for this specific problem, okay? So that's going to be the first and foremost most important thing that you want to do here in this instance, all right? So the question is that, well, how do we go ahead and find these critical values here? Well, that's given to us here in this, well, hopefully given to us somewhat in this problem. What you should do is go to the e-text here if you want to find out these critical values. Again, if you need to, they do might have the chart there. That's nice. They kind of crapped the bed on me. Alright, give me a second. I might have to relog in. Section. Here. Yeah, there. Didn't think so, but had to check. Okay. So what we're gonna do here specifically is let's go over how we can find these values here. You're going to need to go over to page A15 here in the textbook. And A15 is going to have our chi-square distribution chart that we see here on the screen. Now, what we need to do here is take a look at our back of our problem here. And what we need to do here is find out first and foremost what a sample size of 30 has 29 degrees of freedom. So again, remember that degrees of freedom here is equal to n-1. So that's going to equal 30 minus 1, which is equal to 29. We're also given a 90% confidence interval. So because we're given a 90% confidence interval, we have two things kind of going on here. With the 90% confidence interval, we're going to look at 0.9, and we're also going to look at that 0.1. So want that kind of middle 90% here. So let me be sure that that is indeed the case. Unless I have to split that in half. I do the extra double extra sure. Oh, you got the question? Okay. Sorry this is taking a little time. This one takes a little bit of setup to do. Yeah, this problem though, this problem, JD, this one is actually a problem that you didn't do in your class. In 102, you don't cover this particular concept, because this is stuff to do with chi-square distributions, which we didn't talk about. For 120, you extend it out to chi-square distribution. Hence why it looks fairly different. Okay, that's what I gotta do. Nah, it's all good. It's all good. I'm just pointing that out. Okay, so for this one, Natty, all right, let me point this out here. You need to take 1 minus 0.9. You need to take, so you have 90%, and you have basically with 90%, how do I put this way? We're going to take half of that. So we're going to take 90%, take the 10% off of that, and then we'll cut that in half. So we're going to take 100, we'll take 1 minus 0.10, which equals 0.10 divided by 2. Is equal to 1 minus 0.95. 0.05, I should say. So we're going to have 5% on either side, if that makes sense. All right? So let me put it into perspective here. I need to make this make sense so it's not like I'm not confusing myself either. So basically, this is what we're doing, Natty. We have a distribution that, let's say, looks like this. Hey, Ninja! How you doing? Hey, thanks, Ninja. Yeah, I appreciate that, my friend. How are you? I didn't see you online today, so we want this middle 90% here, which means I want 5% here, and I want 5% here. So this is going to be 0.05, and then this is going to be 0.95. Okay. Oh, you got home from the park? Excellent. Just took a nice little stroll around the nice weather here. It's a little chilly here. The audacity to say that to get home from the park? What's wrong with that? That's wonderful. Good. Yeah, it gets a little bit of fresh air out there. Nothing wrong with that. So we're going to look underneath. Oh, the smooth head? That's fine. Nothing wrong with that. It is, I took a 1.5 or 1 on my head. Yeah. Looks clean, right? All right, so my degrees of freedom here specifically is going to be, what were my degrees of freedom that I put? I almost forgot. 29. Okay, 29. So I'm going to have 29 degrees of freedom. Wait, what did you think there, JD? It's fine. I'm not insulted by it. Ninja's a nice dude, like, without question. Without question, he's one of the good ones. Bald? But JD, you know I've been bald for a long time. It's just I have this smattering of hair that's up here. It just kind of comes and goes in little waves, you know, like an ocean. Okay, an ocean of hair, without the rippling effects. You know, it's kind of like one of those still water ponds. That's the best way to put it. All right, so we're going to find our 2 critical values. It rises with the moon. It's so true. All right, Natty, we're going to find 2 critical values. We have our number of degrees of freedom here, which is 29. And we're going to look underneath the 2 columns here that says 0.95 and 0.05. Okay, those are the 2 ones we want to look at. So our 2 critical values here, looking at 29 degrees of freedom here, is going to be 17.708. And we also have the other critical value here of, underneath the 0.05 column here, of 42.557. We're going to mark those down here as well. Okay. Now, admittingly, Natty, you do have to do this by hand. Okay? So that part does kind of stink, but it is what it is. Now, all we have to do here is just follow along what we have for our problem. So that's perfectly fine. So we have n minus 1, which is going to be 30 minus 1. We have our s squared. Now our sample variance here is given to us as 12.8. So we're just going to multiply straight up by 12.8. Okay. And we're going to divide that by 17.708. And then we'll do the same thing here for the other one. Just with a different critical value. So let's do that on the calculator here. Let's see what we get. Okay. Now I'm going to confirm one more thing on my problem here that I kind of forgot. So whether or not I have to take that one extra step. So I'm going to confirm that. So I get how many decimal places now? 2 decimal places. Okay. So we have. All right. So we have here 20.96. Then I repeat this problem here. So I can enter. Let's change this number. So I get 8.72. All right, so I'm going to put both of these numbers down first. I have a feeling these aren't my numbers, but I'm going to check them anyway. All right. Let's check this guy. We have 8.72. And I got that right. Okay, good. That is my answer. And then the next one here would be 20.96. All right, and I got that answer too. Oish. All right, how does increasing the sample size affect the width of the interval? All right, so it's much more narrower. So the width decreases as a result. Okay. And then it says construct a 98% confidence interval. So you're going to repeat this process again with a 98% confidence interval and a sample size of 20. So it's just a repeat again of the first thing that we did. You'll just need to find 2 new critical values in that case, using that and with the degrees of freedom that you had from before. Okay, new degrees of freedom here would be 19, and then you would look underneath 2 new columns here for 98% specifically. You would actually have to look underneath in that instance for like 98%. Yeah, so the numbers are going to change significantly, but if it helps draw out a picture like I have up here, okay, so for example here, yeah, by hand for these problems, unfortunately. So if you're given 98% here, you want 1% over here, and you want 1% over here. So this would be 0.01, and this would be 99%. So those are the 2 columns you want to look underneath, 0.01 and 0.99, with degrees of freedom here in that case to be 19. And then look on the table there on page A19. Or A15, sorry. Ah, why do I get that wrong? All right. Okay, cool. Well, this was the question. Well, hi, Day. This is the question that we were just talking about here. Okay, so this is the question we're talking about here, how to set up the confidence intervals there. Okay, so if you're going to get this problem here, if you're going to get this to be correct, right? So the way we just did this confidence interval problem is exactly how you would want to do like this first question here. It says find the critical values for the 80% confidence level and a sample size of n equals 20. So your degrees of freedom here is 19. In this case, draw a picture, just like I did up here. This time, just change your values here, okay? Hurrah. You're going to have 80% in the middle. That means you want 10% on the left and right, okay? To fulfill the 100%. So you're going to have 0.10 here and 0.90 here. All right? So you just look up on page A15. Why do I keep doing that? All right, that's very annoying. So I'll go back to page A15 here for just a second, which is right here. This is A15. And I'm going to look for those two critical values here, which I need them to be 19 degrees of freedom and 0.10 and 0.90. So 0.90 and 19 degrees of freedom is going to be 11.651. Okay. So 11.651. And my 0.10 here, I'll shift that over, is going to be, I'm going to need to have this whole thing here. 19 and 0.10, 27.204. So 27.204. So if we go back to our problem here, let's go back. What's going to be our first value here? So we're going to have here 11.651. If that's not the answer, do the other one. Okay, so that's the answer for that. And the other one is 27.204. And we got both parts. There you go. There you go, Heidi. That's how you do 9.3 number 1. And then you're going to be applying those critical values to doing the confidence intervals. In those problems, you will need to do them by hand, okay? So be sure to follow the notes there from section 9.3. I'm just saying. I'm just saying. It's part of the process. All right, 10.3, last question there for you, JD. Let's go ahead and put that up. Four in section 4.2, I can do that too. We go ahead and do JD's question here, and then I'll get to that one next. 10.3, last question. Okay. All right, so 10.3 here, last question for you, JD. A golf association requires that golf balls have a diameter of 1.68 inches. All right, to determine if golf balls conform to the standard, random sample of golf balls was selected. Diameters were shown to be in the company data table. Do the golf balls conform to the standards? Use 0.05 level of significance. Okay, so first of all, we have to determine the hypotheses. Okay. Oh, I did yours, Athena? Which one did you ask for? I'm sorry. I accidentally skipped yours. I'm so sorry. You know that's not by intention. I promise you that. I'm terribly sorry about that. Let me go ahead and finish this up. You put up the question. Put up the question that you asked, and I'll do yours, and then I'll do planets after that. As I usually like to do mine in order. Alright, so the mean here is going to be 1.68. That's going to be, that's what we want here. And we want to be sure that the golf balls conform to the standards here, so we can conclude that we can say, okay, does this not equal 1.6 equal 8? Right. That's exactly right. 8.2 question 3, okay, no problem. Alright, so let's check that. That's correct. All right, so for this one here, because we have a mean, okay, JD, what we want to do on the calculator is we're going to do the t test for this one. So we're going to hit the stat key, go over to tests. We're going to do the t test for this one. All right. Actually, let me check that here really fast. Okay, so we did take a sample here. All right. Actually, I'll need to set this up here for just a second. Right. So underneath the t-test, we're going to set up a list with these values in it, okay? So we're going to hit stat. We're going to go to edit. Let's go ahead and clear out these lists here and enter in the list of these golf balls. So we have 1.683 and gotta make that list. Gotta earn that bread. Gotta spread that jam. Let's see here. 1.673. 1.674. All right, there we go. All right. Sorry, I've never heard a guy spread that jam. Hey, look. You have a glut of money. You gotta spread it out. Give it to everyone. No. Save it. That's important. All right, so it's second and mode. Let's hit the stat key. Go back to tests. Keep my jam. Okay. We'll go to data. Now we want the data here to be 1.68. We're going to use list L1, so second and 1. And we have a two-tail test here because it's not equal to, and we'll hit calculate. Okay, and there we're going to get our values that we want here. The test stat here is going to be 0.74. Okay. And the p-value here, 0.476. 3 decimal places. All right, and the p-value clearly is going to be is not less than 0.05. That's not true, so we're not going to reject H0. So there is not sufficient evidence. So there we go, and we got it. All right, and that's how we could do 10.3, number 6. Last question there. No problem. All right, on to Athena's question, then on to Planet's question. 8.3 number 3. Oh, 8.2 number 3, sorry. 8.2 number 3. Let's do it. Okay, so according to a study conducted by a stats organization, proportion of people satisfied are 0.86. Suppose that a random sample of 100 people is collected. All right. Suppose a random sample of 100 people is asked, are you satisfied with the way things are going in your life? Is the response qualitative or quantitative? All right. So the thing is, this would be a qualitative because then you can classify people being satisfied or not. So that would be the first part to your question there, Athena. Explain why the sample proportion is a random variable. Again, this is basically what's the source of the variability. All right, so the sample portion, because value of p varies from sample to sample, that's true. Variability due to the fact that people may must be not. I wonder why they would say not regarding truthful here. People feel differently regarding their satisfaction. That's true. Sample, because the value p represents a random person. And okay. I'm trying to see here. All right, so this would be letter D. The sample proportion D is a random variable because p varies from sample to sample. You could have a different 100 people who have a completely different result. Variability, people feel differently about how satisfied they are. So that would be. Okay, so since the sample size here, okay. All right, what is NP times 1 SP? I gotta do that really quick on the calculator. So you do N times P is 100 times 0.86 times 0.14. This is 12.04. Okay, now, the standard deviation here in letter C is actually really important because what you're going to do is you're going to take, I'll actually put this on the thing. You're going to take 0.86 divided by the square root of 100. Because that's how you adjust the standard deviation in that case. So, oh, I did the wrong one. I did standard deviation divided by the square root of sample size. I was supposed to do P times 1 minus P. Whoops. That is correct, actually. That was not smart of me. Well, that's okay. Yeah, P times 1 minus T divided by 100. And we'll take the square root of that. So let's get that. My fault on that. That should be 0.035. There we go. All right. Okay. Now, let's look at this one here. Letter D. In the sample obtained in part A, what's the probability that people are satisfied exceeds 0.89? Now, the important part here, Athena, is the words exceeds 0.89. Why is that important? Well, because we've just went ahead and said in part C that it's approximately normal. Because it's approximately normal, we can go to our friend here, normal CDF. And since it's above 0.89, we take 0.89. Our upper here is going to be 1 for 100%. Then we'll just take our mean, which we have from our previous part, and our standard deviation from our previous part as well, at 0.035. And we'll paste it down. And we'll see what we get. So here I get 0.1957. And I got it. All right. Any questions about part D, Athena, for right now? We're going to do part E together here as well, but make sure that we got that clear. So can you do second in vars? Second in vars. Okay. Go to second in vars, Athena. Gotta go down to normal CDF. And you gotta do 0.89 because it's exceeding 0.89. So you have to read the problem carefully. If it says exceeds 0.89, it's 89% to 100%. If it's like less than 0.89, it would be 0 to like 89%, for example. So like in this instance, that's why I put 0.89 here in this case. Okay, and I put 1 here as 100%. Then I took the same two numbers I had from here, from the previous part, 0.86 and 0.035, and I put that underneath the normal CDF to get my answer that I just got. Okay? So did you get the answer that associates with your numbers there, Athena? I'll wait until you get that, then we'll move to part E, okay? All right, perfect. All right, got it. Let's go to part E then. It says the probability that 79 or fewer people are satisfied out of the 100 is what? So now this is basically asking the probability of less than 0.79. Okay, that's what we're asking here. So we're going to go back to the well here one more time. Second in vars. Go to normal CDF. Now we're going from 0 to 79%. So 0 and 0.79. And we'll keep these other two guys here exactly the same. Okay. paste that in. So in this case here, we get 0.0228, okay? For my problem anyway, which is unusual because this probability is less than 5%. So again, remember, less than 5% indicates that something is unusual. In this case, this is 2.28%, so definitely less than 5%. So that is what we have here for this problem, and we got it. And that would take care of section 8.2, number 3. Any questions about that, Athena? Hopefully that helps. Give me a second, Heide. I need to do Planet's question here, and then I'll get to your question there. All right. Planet's been waiting very patiently, so I'm gonna get to her question there. All right, so Planet had the question here of 4.2 number 2. Okay, let's do that. No problem, of course. All right. Now, admittingly here, Planet, this one is actually a little bit tricky, okay? This one's kind of a trick question. So I'm going to go through this kind of problem here for 4.2 number 2, as it is a little bit of a trickier question here. So, all right, so here they give you a data of the number of CEOs and, you know, how much money they got compensated by. And then more importantly here, let's go ahead and read this out here. So they give you a total compensation of 10 randomly selected CEOs in 2009. Analysis of the data reveals a correlation coefficient. Now, they give you this correlation coefficient here of R is equal to negative 0.1962. This will be very important for this problem in just a second. So what would the predicted stock return be for whose company made 15 million? What would be the predicted stock return who made 25 million? Now, the important part here does revolve entirely around that correlation coefficient. You have to remember this, Planet, and that says this. It says if the absolute value of R is greater than the critical value, oh, did you get it? Did you take the average of all the Y values? Because that's what you'll need to do for that. Oh, you need question 4. Okay, that's fine. Do question 4. Let's see, which one is this? I'll do a similar question. All right. Let's see here. The least square, the line of best fit is this, where Y is the median income and X is the percentage 25 years and older with a bachelor's degree in the region. Correlation coefficient is 7.353. Pick the median income in which 30% of adults have a bachelor's degree. Okay, so X here is reflective of a percentage, okay? So all you need to do here, this one is just a simple plug and chug type of problem. All we're going to do is just plug in 30 in for X, and we'll see what we get. So let's do it. So 702.9 times 30 plus 15.029. So here we get 17.156. Oh, actually, I think I did that wrong. Check that. Oh, I did. Okay, hang on. I forgot. It's 702.9. I put in wrong one. Sorry about that. There we go. 36.116. Realistic. Okay, got that. In this particular region, 27.6% of adults and older have at least a bachelor's degree. The median income in this region is 31,198. Is this income higher than you would expect? Okay, so for this one here, you need to figure out the expected income, i.e. put in 27.6 in this model. Let's do it. Let's rinse and repeat. Can I type stuff in correctly? That'd be great. All right. So if I repeat this process here, then the expected income here is going to be 34,429. Okay. So this is less than expected because the expected income is 34,000 as opposed to the other way, which says it's 31,000. So that is what we get for part B. Interpret the slope. Okay, so interpreting the slope here is, again, as we know here, the slope here is the rate of change, okay? So the rate of change is reflective of the slope that we have here, okay? So basically, it says for every percentage we go up, we also go up by $702. So essentially, that is what it's saying here. For every percent increase in adults at least a bachelor's degree, the median income increases by $702.90 on average. Okay, so if we check that, that will be perfect. Okay, so that's how we do part C. Now, the last part here can be a little bit tricky, so just talk about it here real quick. Explain why it doesn't make sense to interpret the y-intercept. The reason is because we don't have a value at x is equal to 0. Although it does reflect a y-intercept, 0 is not within our value in our data set, right? Our minimum here is like 15, like a little bit touch above 20% of people having bachelor's degrees or whatever. But we don't have anything at 0%. So it doesn't make any sense at all. 0 is outside the scope of the model. Like if you have no bachelor's degree, okay. So the x value is outside the scope of the model, and I'm going to check that, and we got that correct. So if it's within the scope of the model, we could do it, but it's not within the scope of the model because that's what the scatter plot tells us. So that's why the answer here is letter B for that part D. And that is section 4.2, number 4. Any questions, Planet, before I move forward? The next question, at least. You're welcome, of course. Now, I was asked by Hyde, 9.4, question 1. Okay. Well, okay. So a simple random sample of n for 50. 27 people said they, okay. All right, so the test that you have to use for this is not a test, actually. This one here is a confidence interval problem here, Hyde. So for this one here specifically, you're going to need to use, let's go to, yeah, this is confidence interval because they want a lower bound and upper bound. Notice it says a 99% confidence interval here. So what you'll need to do is you need to go down to number 5, which says, not number 5, I'm sorry. Where is it? Letter A. 1 prop z int. No, not t interval. 1 prop z int. The reason is because you're given a population proportion. So Hyde, you have to read these problems carefully because this says population proportion. This is not just giving you a mean here, it's giving you a proportion. Okay? So that's why I have to use letter A here. And then I put in the numbers appropriately, and I can just pretty much go ahead and quickly find out what this is. And I round to 3 decimal places. Got it. Upper bound. Let's do it. And I got it. All right. And that's what you got to do here for 9.4, number 1. Remember, section 9.4 is a summarization section for all the other 3 sections. So I just gave a sample problem from each section. And then just kind of having you review some of those problems. So no problem. It's okay if you feel slow right now. You're going to start picking it up as you start to review stuff. So, you know, that's what it's there for. Not a problem. I'm slow too. So you're in good company. All right. All right. That was that question right there. Very good. Do you have any other questions? So the Agresti and Cools method is just a very specialized case for small sample sizes. So that one was with the square root of the normal way to do it. If you're not using Agresti and Cools with small sample sizes, would be the p times 1 minus p divided by n, right? If you wanted to do that standard deviation, Natty. So that was a very specialized question, or a couple questions used that, but the ones on the test won't use that, I don't think. So, it's on the practice test? Oh, okay. Wasn't my intention to put that on the practice test. Shoot. Can't really swap out questions now. Can't really swap out questions now. I didn't want to put that question on the test. I thought I went over the questions carefully, one at a time. Well, that's kind of sad. That's okay. It's question 2. That's okay, it happens. I can always switch the test around anyway. That was on question 2. Was that... that wasn't here. No, that wasn't this. That was, oh, it's question... Oh, okay. Here we go. Well, let's do it together anyway. This isn't as bad as you may think it is, as you may see it is, so let's do it together. Here's question 2 from the practice test right here. Okay. Alright. So in this case here, Jade must estimate people who eat cauliflower. 3 out of 28 say they do. You want to do a 90% confidence level. Alright, so for this one here, you just have to put the pieces together. So if you see, hey, I want to do the Agresti and Cools method, just start putting the pieces together carefully, okay? Otherwise, you're going to make it harder on yourself if you try and do it all at once. So just do it in pieces at the end of the day. The best way to kind of approach this particular problem is if you have a lower bound and an upper bound. So this is what you see here. So it says, okay, do a p tilde here. P tilde here is x plus 2 over n plus 4. Just do that first. So x plus 2 is x the amount of people who said yes. So that's 3 plus 2 over n plus 4, which is 28 plus 4. So that's going to be 5 over 32 in this particular, with these numbers. Fine. Okay, now we'll come back and we're going to use this here in just a second when we do this stuff here for the plus and minus. So we have a 90% confidence interval, so we need a critical value that goes with that. So a critical value with 90% is going to be, let's go ahead and check that. What was that? 1.645. Yep. Just using a thing from the back of the book here, but so critical value for 1.645. And here we're going to go ahead and say, all right, here we have 1.645. Oops. So here we have 1.645 times our value here of 5. So let's times the square root of, then we're going to have the square root of 5 over 32 times 1 minus 5 over 32 divided by 28 plus 4. Now, one thing I suggest is to do is that if you're going to get this right, if this is going to be tough, then figure out what this is first. Okay, this is the ugly part. So we're going to figure out what this is first. Now, in order to do that, on the calculator here, it looks very ugly, but as we've talked about here, if things look ugly, do it in parts, okay? Don't try and do it all at once. So what I mean by doing it by parts is, let's just do it one piece at a time. So I'm putting parentheses here, 5 over 32 times 1 minus, and in parentheses again, 5 over 32. Let's just do it one piece at a time. And then let's divide by, in parentheses here, 28 plus 4. Okay? And then I just want to take the square root of that. So second and square root, and second and the previous answer. And we get this. And then all we want to do is multiply that by 1.645. And we're going to write down this, this exact thing right below. 0.1055. Let's write down this whole decimal. 863602. So you notice how long that took me? That didn't take me very long to find that big old ugly mess that you thought it was really hard. I just plotted along one step at a time. So again, if you try and put it in all at the same time, yes, it's going to be terrible, and it's gonna be really, really bad. Okay. Yeah, so we have one on the homework here. I could have sworn I took, well, at least I thought I took it out. Do something here though. Okay, I'm gonna do. All right, I'm gonna do you guys a solid here because I didn't want that to happen, in all honesty. In all honesty, I didn't want that to happen, so... So let me go over this carefully then. Hang on a sec. I have to be fair, so I didn't really go over that method at all, so I'm not gonna be like, no, not that one. Lord, fair problem. Oh. Did I answer that? Okay, that one's okay. 7. Yeah. All right. Okay. 27. But do 27. Check that here. 27 for that. Edit. Okay. All right, there we go. All right, so what I went ahead and did is, all right, let me go ahead and explain what I did there. What I went ahead and did is I replaced that question, so that should no longer appear on the practice test. If you try another new practice test, then that second question won't be using that method there. So I put in a different question that doesn't use that method. So you can now it should be just kind of like the regular stuff. So I didn't mean to put that question there, but I replaced that question. If there's any other questions that kind of pop up like that, please bring it to my attention. Because that wasn't my intention to do that. Yeah, that method will not be on the test. I just took it out. That's what I was working on for like those 5 minutes. So I just took it out of the practice test and the real test, so you should be fine. See, when you bring it to my attention, sometimes I'll miss things like that. It's fine. I'm only human, but I will make corrections as necessary to make it fair for everyone. So yeah, you're only 2 questions into it, so that shouldn't be a problem. 4-1 question 6. Okay, let's do it. You know you can take the practice test as many times as you want, so it's not like it's a super big deal, which is good. Oops, I put it the wrong way. Alright. 4-1. 4-1, number 6. Alright. This will probably be my last question here today. You can take the Heide. You can take the practice test as many times as you want. So it's really helpful because then you'll know exactly what to expect for the real exam. All right. Researchers wondered the size of a person's brain related to individual's mental capacity. Okay. So they measured the MRI counts and IQ scores. All right, fine. Data is reported to the right. Complete A through D. Okay, so it's either A or B, A, B, C, or D, I should say. Make this bigger. So based on the data, is it A, B, C, or D for the scatter plot? Let's take a look. I always look at the more extreme ones here. So looks like the ones that's like 1,080,000. It's like 141. Usually take it once and I'm good. All right, if that works for you, that is not a problem. So we want the MRIs to be X and the IQs to be Y. So it has to be, can't be C or D, it has to be A or B. Okay, the answer is B. If you notice here, this 140 for the extreme value, but this one is slightly above 140. It says 141. All right. All right, that's correct. All right. Compute the linear correlation coefficient between MRI and IQ count. Are they linear related? Yes or no? All right, let's figure it out. Why not? Let us see. I don't know. We're gonna actually copy down that table. Actually, there. Let's copy down the table in our list of stuffs. Okay. Okay. So 816932, 833, 868, 856, 7, 9619, 857, 82, 949, 395, 0s, 2, 7, 9, 2, 4, 9, 9. Okay, and we'll put in our IQs. We don't combine the list. I'm putting it as an XY thing. So X for the MRIs, Y's for the IQ, JD. We're just going to find the linear correlation coefficient here. Now to do that, in this case, we're just going to go again. We'll hit the stat key here. Actually, I make sure about my list. I didn't do anything. Okay, I didn't enter anything bad. All right, so second quit. Let's go to stat. Let's go to calc. We'll go down to linreg ax plus b. We have our x list to be L1. We have our y list to be L2. And we hit calculate. And there we can see our R here, which is 0.695. Now we need to also figure out if there is a linear correlation We're going to need the critical values for this. So 695 is a touch above our critical value here of 0.632. So because that's the case, there is a linear relation with our correlation coefficient being 695. Again, the correlation coefficient, in order to have linear relation, right? Linear relation equals if the absolute value of R here is bigger than the critical value. And remember, that's based on sample size. That's why they give you this little list here to view the critical values. And if I check it, then I'm correct. Okay. Okay. Change the scatter diagram to use a different plotting system for each gender. Okay. Let the fuchsia triangles represent females. Fuchsia. Ooh. Blue circles represent males. Which scatter diagram? Both sets of data plotted on the same axes. What? Okay. Hang on. I need to look at this. All right. We have females and males, right? So we have 5. We have like should have 5 and 5. All right. Fine. So it's basically part A, just with a different thing. Okay. So where's our winner? All right, it's still letter B. Okay, fine. I don't know why you asked this question. It's dumb. All right. That question is so dumb, I can't even fathom that. All right. Compute the linear correlation between MRI and IQ for females. So that was the first. That was the lowest 5 values, and then the ones for males. Okay, so in this case, all they want us to do is take the lowest 5 values to be the females and the higher 5 values to be the males. Okay. Fine. And that's what you want us to do? That's okay. Go back to our lists. Let's make up 2 more lists. So let's make up some new lists here, actually. Let's take the lowest 5 values for the MRIs. So lowest value 790, 619, 135. 790. Let's see, what's the next one? 816, 932. Oh, they're all the lowest, aren't they? So the left side is females. Oh, the left side is females. Oh, no wonder. Okay. I'm reading that wrong. So the whole left side is females and the right side is males. I still think it's dumb, but whatever. Okay. Just don't see a version why you have to kind of separate it out. Yeah, it is dumb. Just because it's like, yeah, I see why you're doing it in terms of the basis of the question, but it's like, well, you know, you already kind of asked the question from the first part, so it's like, why are you asking again? It doesn't make any sense. So, I like avoiding dumb questions. I'm not very pleased about how this question is phrased. Okay, so here are our IQ values here for each person, respectively. L1, L2 for females, L3, L4 for males. Alright, so we're going to go ahead and hit the stat key here, go to calc, we're going to go to linreg ax plus b. Let's do the females first. That's with L1, L2. Our correlation here for the females is going to be 0.258. And for the males, we're going to do the same thing again. Hit the stat key, go to calc, go to linreg ax plus b. This time, change your x list and y list respectively. 2nd and 3 for L3, 2nd and 4 for L4. So we had to split those lists up. Calculate that. And here we get 0.321. Okay. And we got it. So are MRI and IQ count linear related? Because the correlation, so it's positive, and the absolute. This is a really bad question. This probably is one of the worst questions I've seen. All right. What is our critical value for 5? 0.878. Fine. All right. No relation exists because it's not greater than 0.878. The coefficient is positive. The absolute value is 0.321. This is not greater than 0.878. No relation exists for males. Okay. Alright, fine. That was absolutely ridiculously dumb. That was a waste. Alright, anyway, that's not really hard. Alright, but, well, despite ending on the not so greatest of questions, alright, that's the last question I'm going to take here for today. But, um, I want to thank everyone for coming on out here to the stream once again. You guys took up all my time. Thank you very much for all the questions. Of course, we're going to be taking more questions on Monday. That will be probably questions for the final exam because the test here for the third test is going to be due for both classes is going to be due in 4 days. So be sure to finish it by then. Thank you all so very much. I love you all. All of you are wonderful, wonderful people. Thank you for sticking with me for this whole time. Um, as always, everybody, stay safe, stay healthy, and most importantly, stay sane. All right, have yourself a wonderful night, everyone. Get a chance to relax away from doing numbers and math for a little bit, and then get right back to it. And hopefully, I wish you good luck here on this next exam. All right, I will talk to you on Monday. I may have some free time for some questions tomorrow, as I'll be on tomorrow at 5 p.m. for my 97 class. But if you want to drop in and ask a few more questions in regards to that, I'll be on at 5 p.m. just in case if I have a little bit of time to answer some of those. So a little bit of extra time before the weekends. All right, take care, everybody, and we will see you on Monday if I don't see you tomorrow. All right, have yourself a great one. Take care of yourself. See you later, everybody. Bye.